All right, so today's video is going to cover section 6.3. It's our first day of the section. And what section 6.3 is going to cover is very important. We are learning a new type of function today, and this is called an exponential function. So to help us understand and learn about exponential functions, first we're going to focus on linear functions because we know them already. And what we can do about linear function is look for some patterns and some general knowledge about that so that we can then use that to help us learn about exponential functions. So here's the definition of a linear function. We know a linear function can be written in the form that I have here, and we call this slope-intercept form. There's other forms of a line, which we'll address later, but for right now, this is kind of like our basic form of a line. So we know a few things about it already. We know that m, for instance, is our slope, and then we know that the b value there is the y-intercept. So I'm just labeling those right now, and I would expect that you do the same on your notes. And just the definition of the y-intercept, just so we're clear, this is the y value when x is 0. So what we know about lines already is, first of all, they make non-vertical lines on a graph. So a linear function is a non-vertical line. So for instance, like this first picture I have, this is a positive slope. So I'm just going to put positive m. This would be an example of a negative slope, so a negative m value. And then this is no slope, or in other words, the slope is 0. We know a vertical line is not a linear function. It doesn't pass the vertical line test, so that's why that's not included here. Now, the most important thing that we're going to learn today about a line, or remember about a line, is that a line has a constant rate of change. Now that's super, super, super important, but what that means to us, what is a constant rate of change? We have this little sentence to help remind us. Every time x changes by some sort of number, the y value is always going to be increased or decreased by some amount. And what we're saying about that is the amount that it's increased or decreased is the same every time. So I've generalized that to say, as we change the x values in a table or in a linear pattern, we should see a pattern involving addition or subtraction in the y values. So let's look at what that means here. So we have this table here, and what we can see in the x values is that the x values are increasing by 1. So then what we see, and again, maybe I'll just label this table as linear so we know that it is linear. So if I change x by 1, what I'm noticing is that the y values are increasing by 2. So every time I change x by 1, the y value is always changing by a constant amount. So with that, then we'd be able to write an equation, right? We know y would equal, in this case, 2x, because that's our slope, and then our y-intercept, when x is 0, would be 3. Now, our goal for today is to connect a little bit more information about the slope and the y-intercept. So what we notice about the slope is that the slope is the change that we see in y when x is changed by 1. So I would ask us to note that on our notes. Another way of thinking about it, the slope is also the change to the y values, but specifically it's the change to the y values if we change x by 1. And then what we can see about the y-intercept, the language I'd like to introduce today to help us think about exponential functions, we like to think about x equals 0 as the initial x value, or like the starting x value. And a way that I remember that is like a stopwatch. If I'm timing something, the time starts at 0. So when we see the y-intercept, is the value when x equals 0, another way we can think about this as the starting y value. So when I look at this equation, it says start. And what I mean by start is when x equals 0, start with the y value of 3. And then when I see this 2 in front of the x, it says add 2 to y if x changes by 1. And that's how we want to interpret the equation of a line. So for instance, if I made a change to x by 1, which would bring me to 4, then according to the equation, I should make a change to y that is 2. So if I started at the y value of 3, every time I increase x by 1, I increase the y value by 2. So let's look at a few more of those. Like with something like this, if we see the y-intercept here, we can see that x is changing by 1 every time. And what's happening to the y values? Well, they're decreasing by 15. And we can see the pattern is involving addition or subtraction. So we know this is linear. So the equation here would be y equals. So if I change x by 1, the y values are decreasing by 15. So we get negative 15x, and then our y-intercept was plus 20. Now with a linear table where the change isn't 1, we need to calculate our slope first. Right, so here I can see that the x's are changing by 3. So every time that x is changing by 3, I still see a constant pattern in the y values. So every time I do the same thing to x, I still see the same change to y. But for the equation, we want our change to be 1. So we know what to do with our slope is just to divide the change in y over the change in x. So we get this slope of 2. So y would equal negative 2x, and then plus our b value. So what would our b value be? Well, we could use the pattern, right? If I decrease this by 3, then this would also, instead of decreasing by 6, it would go backwards. So it would start at 42. Or if I guessed, if this x was 0, if I increased it by 3, according to my pattern, the y value should be decreasing by 6, and that does work. So we can see our equation would be negative 2x plus 42. Now with something like this, what we can see is when we see linear patterns, right, I can see I have the y-intercept. So in my equation, y equals something x minus 6. And if I'm looking for the slope, it's what is the change by 1. So if x goes up by 1, I can see that the y values went up by 3. So I'm guessing my slope should be 3. Now, what's the problem there is that in the table, not all the changes are 1. So like here, I saw that x went up 8. So if I made this change, if I changed x once, and I'd have to change y by plus 3, what if I did that 8 times? Well, 8 of those changes should be an increase in 24. So I can see that that would reduce to the same slope. So here, the increase was 4. So if I increase x by 1, I would add 3 to y. So let's do that 4 times. I would add 3 to y, I would add 3 to y, I would add 3 to y, and I would add 3 to y. We can see that'd be adding 12, which brings us there. So again, for our linear pattern, we have a constant addition or subtraction change if x is changing by 1. Now, as we transition to an exponential function does not have a constant change. Instead, what we have is this thing called a constant ratio, or sometimes referred to as a constant multiplier. So an exponential function has a few different letters. It's called a times b to the x, and this value of b has nothing to do with this value of b. So please don't confuse the two. But what we know about or what we're going to learn about an exponential function is an exponential function creates what we call an exponential curve. So it's not a line, it's not straight, it's a curved shape, and there's a lot of different examples, and we'll talk more about the graphs in day 2 of the notes, so let's kind of go past that a little bit. But what we want to know with an exponential relationship is what we see is every time we change the x value, we should see some sort of pattern in the y values that involves multiplication. So let's compare and contrast these tables here. So if this is an exponential function, what I'm noticing is the x values are always going up by 1. However, when I look at the y values, the change is not constant. Here the change went up by 4, but here the y values went up by 8, and then they went up by 16. So I can see that y, the amount I'm adding or subtracting to y, is not constant every time, compared to a linear function where it is the same every time. So if our change is not a constant addition or subtraction, we know that we might think of it as an exponential function. And an exponential function, addition or subtraction won't be the pattern. We should be looking for some sort of pattern involving multiplication. So what I notice is if I started at 4, I would multiply that by 2 to get to 8. If I took 8 and multiplied that by 2, I get 16. And likewise, 16 times 2 is also 32. So I can see that this table has a pattern of multiplication. So this brings us back to our equation. And the equation of this table would actually be y equals 4 times 2 to the power of x. So what does that mean for us? In our equation up here, the a value is actually the starting value of an exponential function. So we call this the start value. Specifically, what that means is this is the y value when x is equal to 0. Now, what the b value is, the b value for us is going to be called our constant multiplier. And what this really means is this is what we multiply y by. We multiply that if the change in x is 1. So let's go back and kind of reanalyze that equation that we wrote. So this 4 value is supposed to be the y value when x is equal to 0. So we can see that here. So I view this as the table starting at 4. And then what we realize this times 2 is that's what we're doing every time to get the new y value. So we can view this as starting at 4 and repeatedly or over and over multiplying by 2. So that's the general idea for an exponential function. We need to find what is the constant multiplier. So if we look at this one, let's try that again. The first thing I notice is that the x values are changing by 1, which is good because in our equation, if we wanted to find that constant multiplier, the constant multiplier, or the number in the equation, is only what we multiply by if we change x by 1. So when I look at this, if I'm thinking, what did I multiply 8 by to get to 4? So I'm thinking 8 times what would equal 4? And then what did I take 4 by? What did I multiply that to get to 2? So here we introduce the word constant ratio. And the constant ratio helps find the constant multiplier. Now we'll notice that I didn't say it is the constant multiplier. I just want you to know that it helps us find the constant multiplier. So in the next few examples, we will see how that constant ratio isn't always the constant multiplier. But what the constant ratio is we divide consecutive. Remember, consecutive means in order. And the x's need to be in order is what we mean by that. So we divide consecutive y values and reduce. So for instance, if I wanted to know what did I multiply 8 by to get to 4, I would take the 4 and I would divide it by the 8. So I would take 4 and I would divide it by 8, and if I reduce that, I get 1/2. Now the reason that this constant ratio is the constant multiplier is because we're saying this happens if x changes by 1. So that's a special case here. So what we're noticing here is that because x is changing by 1, I notice that if I multiply all the y values by 1/2, I always get to the next one. So our equation here for this one, if we summarize, would be y equals. Now a is where our table starts. So we can see that it starts at 8 because the x value is 0, and I'm repeatedly multiplying by 1/2 over and over and over again. Now let's look at that constant ratio and how it can be a little bit different here. So what I notice here is the change in x is no longer 1. The change in x is now 3. So let's see how that works and what does that tell us for our constant multiplier. So if we started with our constant ratio, what I would do is I would take 2 consecutive y values. So I'd take the second one and divide it by the one before it. Right? We can see our x's are in order. So if I started with 64, I would divide it by the previous term. So my constant ratio would be 64 over 8. And we know 64 over 8 is equal to 8. But the change in x was 3. So what I'd want us to visualize here is I'm going to create our table a little bit bigger. If I started at 3 for the x value, we know that the y value was 8. Now we skipped a bunch. So we skipped 4, we skipped 5, and then we ended up at 6, and we got to 64. So what I'm wondering by is what did I start at 8? I multiplied it by something for 4, for 5, and for 6, and I ended up at 64. So what I want to know is what did I put in each of these boxes, and each of those boxes together should be an 8, right? Because I know 8 times 8 is equal to 64. So in other words, what I'm asking myself here is what did I multiply 3 times in a row to get 8? And that is the definition of our roots, and that's how we studied that early. So what did I multiply 3 times in a row to get 8? Well, that number is 2. So if I fill those in the boxes, I would see that this math would work, right? 8 times 2 is 16, times 2 is 32, times 2 is 64. So I could fill this in my table, 16, 32, and 64. Now in this table, my change in x is 1, and I can see that my constant multiplier is now 2. So the equation here would start y equals a times b to the x, and we know that our constant multiplier is now going to be 2. So the constant ratio, we're noticing that the constant ratio is related to roots, right? The change in x is what root we need to take. So for this last thing, though, we do need to find our a value. So we could just continue the pattern. What I noticed is if I change x by 3, so if x here is 0, I would have increased it by 3 to get to 3. What we can see in this table is that if I'm changing x by 3, I'm always multiplying by 8. So what was here that I multiplied by 8 to get to 8? Well, that must have been 1. Or we could break it down into smaller steps, right? We could put a 2 and say, well, that must have been a 4. We could put a 1, say that must have been a 2, and then at 0, we must have had a y value of 1. So our last example for today, let's put that all together. So what we notice here is that x does have a few different changes. Like right here, I guess it goes up by 1. Here it goes up by 2, and then here it goes up by 3. Now I'm telling you that this is an exponential table because I made the notes here. So if it is exponential, let's try to write our equation. What we would notice is we do have the starting value of the table, right? If x is 0, y is 5. So we know that is our a value. I'm sorry, I forgot to write that example up here. Our a value up here is 1. So let's just do that right now. But here, what we see is if x is 0, our y value is 5. So we have to figure out is what is our constant multiplier? And remember, this number is what we multiply y by if x changes by 1. So what we see here is, well, this is where x changes by 1. It increased by 1. So what did I multiply 5 by to get to 10? Well, that must have been 2. I just want us to see again how we could do that in a slightly different way. If I calculated my constant ratio between these two terms, I would take the y value of 40 and divide it by the y value of 10, which is equal to 4. But the change in x between those two was 2, which means I would need to take the second root to get my constant multiplier. Because what I'm saying is I started at 10 when x was equal to 1. I skipped x equals 2, and then I ended up at x equals 3, and I was at 40. So I did 2 stages of multiplication there. I multiplied it to get to this number, and then I multiplied it to get to that number. So I'm asking, what did I multiply twice in a row? So if I started at 10, and I multiplied by something twice in a row, and I ended at 40, well, that must have been 2, right? And the square root of 4 is 2. Oops. So this would have been 20 if I multiplied by 2. So again, we could use that to fill in the blanks, right? If I know that I'm always multiplying by 2, if x was 4, I'd be at 80. If x was 5, I'd be at 160. We could also see that constant ratio one more time. If I looked between these two y values, if I took 320 and divided that by 40, I get 8. But the change in x between those y values was actually 3. So the cubed root of 8 would be 2, and that is our constant multiplier.